Thank you very much. I mainly work with Bishop sets, which are, in order to define a Bishop set, you do it somehow like you define a category. So you say first the objects, what the objects of the set are, you say when two objects are equal, and then you prove that the equality relation is an equivalence relation. So this is the pattern which we all know from category theory. And Bishop set theory is, it was recognized by Eric Palmgren in 2012 that it had a lot to do with Lovier's elementary theory of the category of sets. And Palmgren provide a constructive and predicative version of ETCS in order to give a categorical model of Bishop sets. Now, Bishop sets, or Bishop set theory, is very close to Martin-Lev-type theory. I won't talk now about the connections. Actually, Bishop's book motivated a lot Martin Lev, although he had already written his PhD on constructive mathematics in 1968, without knowing Bishop's book. But there's a common feature in these two theories, which is very important. They have dependency as a fundamental concept. And dependent types, let's see the type version of dependency. You start with a type in the universe. We have a type family, a family of types over A. And a dependent function is just a section. Here is the type. And here are some elements, A and B. Here are the spaces P of A, P of B, and so on. And a dependent function is just a section. It picks an element from every P of A for every A in the type. So such a thing, which generalizes the concept of a function when the family of types is constant, such a notion is fundamental in these systems, in type theory and Bishop set theory. While even to discuss families of sets in ZF and CZF, you need replacement. So this feature makes the implementation of category theory very natural in the systems, because the basic concepts of category theory, functors, natural transformations, are dependent notions. On the other hand, we use category theory to understand, to model Martin-Lev type theory. Even for a topos, especially for a topos, we have the Mitchell-Benabou language, which suits so nice. It represents the types in a natural way. So there are many connections here and here. My starting point is the following. My starting question is the following. I would like to have a concept of dependent arrow which is to the concept of dependent function what the concept of arrow is to the concept of function. Now, there are many models of type theory, but you need to know a lot of type theory to understand them. And they are very complex. See, for example, categories with families, because they want to implement the whole syntax, which is not trivial. If this notion is very fundamental, and I think it is, it has to have a very simple categorical interpretation, similar to the way arrows generalize functions. And how do arrows generalize functions? They do it in three ways, I would say. Arrows preserve, arrows forget, and arrows add. So by this, I mean the following. So arrows, of course, have some basic properties of functions, the axioms of category. If you have a terminal object, they preserve elements, but they forget some properties. For example, we don't have arrow extensionality for all categories. But what is important is that arrows add properties that we cannot trace to the prototype. And this is duality. In sets, a non-empty set has no global coelement. But here in category theory, we have global coelements, we have interesting categories where the co-elements are important. For example, in the category of Boolean algebras, with initial element, the Booleans, the coelements correspond to algebra filters. In the category of rings, where the initial element is the ring of integers, this corresponds to prime ideals and all that. So we have new information. And also, we can repeat the pattern. We have higher structures. So we would like to have a notion of dependent error that preserves, forgets, and adds in a similar way. And without knowing type theory, just to understand this thing and make it understand that this is fundamental. In order to do that, we add to the errors of the category two structures. We add, the structure of family errors and then the family of dependent errors. And we can go on. We can go on and have a higher categorical structure of dependent errors. So how to do that? First we say that for every object in a category, we associate a given totality, whatever, of family errors. So we say that something starts from A, or this is just a picture. It could end to A. But you specify a family of objects, a set of objects, or a class of objects, that you call them family errors on A. And this has a composition with the standard errors that respects the properties, the definition of the category theory. So you want lambda composition with 1A to be lambda and to be associative. So we have two compositions here, the composition of arrows and the composition of the family arrow. If you go to the paper of Pitts from 2000, Categorical Logic in the Handbook of Computer Science, there he defines type categories, a variation of Cardinal's categories with attributes. And he defines family arrows on a topos as pairs, elements of the objects of the category, and arrows from the product AB to the subordinate classifier. And the composition is defined in a natural way. Now, not every family arrow starts from A. It could go to A. For example, if you take Seeley's paper and take the slice, and then you take the pullback of lambda over F, this is the composition. But then you miss the strict conditions, the equalities that I mentioned. And there is an old discussion between Benabou and Erard and other people like Pitts that advanced the strict approach rather than the weaker one, but more general one of Benabou and Erard without strict conditions. Now, family arrows preserve and forget properties of families of types, as expected. And there, before saying what a dependent arrow is, I would just say how you define sigma objects, which correspond to the sigma type, the existential in type theory. So having a family arrow lambda on A, you define a specific object, you call it the sigma A lambda, and an arrow projection on lambda, such that this is a pullback for every arrow F. And this is something that you always have in type theory or in sigma situations. And you talk about a category with family arrows and sigma objects, and that they satisfy the obvious strictness conditions. If you take 1A, this would be the 1 of the sigma A lambda, because this is lambda again, and you have the appropriate composition strictness condition. So in the paper of Pitts, he calls type categories what we call here fam sigma categories with a terminal object. So fam categories with sigma objects on them and a terminal object. And these are just like Hartmann's categories with attributes. Now, it makes sense to have categories with fam sigma categories without a terminal object. For type theoretical reasons, you want to have a representation of the empty context and you need the terminal. But you can define nice and interesting categories where there are fam sigma categories but without a terminal object. I won't get into the details. But in this category, you take the commutative ring, the additive structure, you take the singleton, and you have the category over that. And every commutative diagram here is a pullback, and the families are the pairs, you have a composition and you make it a thumb sigma category, but in general, there is no terminal object because the ring has many objects, many elements. In the case of constant family arrows, the family arrows are just the elements of the category, the sigma is just the product, and the projection is the projection to A, as expected. And you can define the sigma objects on the topos. This is again a definition of Pitts. You take the pullback of the arrow with a true arrow. Now, we can repeat the pattern. What is a dependent arrow in this simple abstract word? You have a specific A and a given lambda family arrow on A. And you just say which are the dependent arrows. As you say, which are the home sets. But you also have a composition of the dependent arrows with the arrows, such that the obvious compatibility conditions hold. This means a dependent function, a dependent arrow composed with one A is again the same over lambda, and you have a specific composition, phi composition F with G, it's just phi composition F with G, and all the lambdas here over the corresponding family arrows which are true from the family structure. So dependent arrows preserve and forget properties of dependent functions. So every element I, global element, goes to some element of lambda I, but we don't have dependent arrow extensionality. And any category can be turned into a dep-category. Just take the constant family arrows and define as dependent arrows the arrows. As in the case of types, where if the constant type family is considered, the dependent functions are just the functions. Now, any thumb sigma category is turned into a dep-category. You can define canonical dependent arrows. Just take the arrows from A to the sigma object, this is composed with the projection and gives you 1A. These are exactly the dependent objects that one finds in the paper of Streicher and Hoffman on the groupoid interpretation of type theory. And a student of mine gave another representation of the canonical dependent arrows on a topos. I can't get into the details, but the proof is not trivial. Now, there are depth structures that are not induced by the canonical thumb sigma structure. So in the case of the ring, which is a category over its adjective structure, the dependent functions in the canonical way are just singletons minus AB, but we can take as the ideals of R that have A minus B and that ideal to be a dependent function, this dependent arrow in this sense. And of course, there are many ideals in many rings that contain a given element. Now, the sigma type in type theory is determined by its first projection and its second projection. But its second projection, you see, is a dependent function. And now, having dependent arrows, we can define the second projection as a dependent arrow in a thumb sigma category. It is just a certain dependent arrow over this composite family arrow, and we need to have some compatibility condition, some strictness condition with respect to the basic pullback. And in the case of constant families, this projection is going to be just the second projection, as expected. And now every thumb sigma category is not only a dep-category, but you can define a natural canonical second projection arrow, dependent arrow in the structure, by taking this construction here, which is not trivial to explain in a few seconds. But again, there are dep-sigma structures that are not induced by the thumb sigma structures, and again, we can use the simple example of the commutative ring, where we have a non-canonical dep structure, which is the set of ideals, and the projection here is just the ideal generated by A minus B. Now, if you take a fam sigma category, and you can define another category, the category of sigma objects, and arrows the pairs F and sigma F that makes this rectangular pullback, then we have a generalization of the growth of the construction. The projection one, it can be defined from this new category to the initial C, such that this projection is a split fibration with a splitting cleavage. And the proof that it's a splitting requires to use the strictness conditions of fam sigma category that we said at the beginning. Now, what is that we added, that we can add, that is not traced to the prototype with dependent functions? And we want to have some kind of duality generated out of this framework. And the duality is natural and simple. We have co-family arrows, co-sigma objects, and co-dependent arrows. And we can, again, make more of these dimensions. So a co-family arrow is just, you can imagine that you can picture the co-family arrow as something that goes to A, not starts from A. And you compose it now in the other way with the arrows, and the composition and the obvious rules hold. And you can take, again, as co-family arrow and as given category, the objects, and F composition with B is just B again. In a co-family, in a topos, you can just reverse the previous construction of pits and talk about coproducts and things that go from omega to the coproduct rather than going to omega. Again, we can reverse the example of Sealy and talk about weak co-family arrows on a category with push-outs. Similar things, we have co-family arrow extensionality property that may not hold, so we lose some things sometimes. But we have for free the notion of co-sigma object in a category with co-family arrows. We're just turning the pullback condition that we've had for the sigma objects to push-out condition. And in the case of sets, for example, you can take the Q object. You can take as arrow any function from X to A. This is the co-family arrow. And the Q object, the co-sigma, is the set of fibers. The injection, 1, is just the function that takes A to the fiber of A. And this turns out to be a push-out. So the category of sets is a co-fam, co-sigma category in this sense. If you take the category of rings, and you take the ring epimorphisms, the Q objects, if you take the family to be the co-family arrow to be the set of ideals of R, then the co-sigma object over the R and I is just a quotient. And that's why I chose the notation of Q, because somehow the co-sigma object is a generalization of the Q, of the quotient construction. If your category has binary coproducts and B is a constant co-family arrow, Q of AB is just the coproduct, and the injection 1 is just the injection 1 of the co-sigma condition. Again, you can have co-sigma objects on a topos by just dualizing the example of pits. And now, categories with codependent arrows. You have a specific A and a specific co-family arrow, and you just say what are going to be the co-family arrows, the codependent arrows. And you define a composition with the usual arrows. You, of course, put the dual conditions, the dual to the conditions we had for dependent arrows. And all the theorems that we had in the picture of the dependent picture can be dualized, and the proofs also. Namely, any co-fam Q category is a codep-category, where you have the obvious dualization construction, the dual construction. but the proof is also the dual one. You need to do nothing. But more importantly, surprisingly, you can talk in a natural way about the second injection. So you take the second projection construction definition, you dualize it, you put the corresponding strictness condition, and now you have the notion of second injection for as a codependent arrow. Again, you can prove that any cofam Q category is a codep Q category in a canonical way. So what we did was to show that if you have this concept, you have a simple, maybe simplistic, but very, for me, very natural approach to the concept of dependent arrow that mimics the way you define arrows in a category. You have a way to combine dependent and codependent features in a categorical way. And you can actually work with some of these dimensions together, not separately. Let me give you an example of that. If you take the category of small types in the universe, in the hierarchy of growth-fitting universes in type theory, this is already, as I said, a category with dependent arrows, which are the dependent functions that were here. But now you can take, you can make this category a codep category by doing the following. To every object, you say that the cofamily arrows are the elements. It's the object again, are the elements of this object. And the codependent arrows is just the path space, the loop space from A to A. Of course, the composition F with P is just the application of F on the proof that A is equal to A. And this is a codep structure on the universe, on the category of small types, but it is not deduced by the following canonical Q structure on U. So the canonical quotient objects are, you take a given type, a cofamily arrow here, an element of A, and you take the type A product, the singlet of A. The injection is this map, this injection 2 is this map, but this cosigma structure is the canonical one is not capturing the previous one. So this is a new one. And of course you can imagine, you can do higher codependencies by taking now proofs that the loop space of the proofs that f of A is equal to A and so on. The proofs that Q and P are equal, where Q and P are proofs of that A is equal to A, and so on. So all these higher dependencies, all these repeated patterns that we have in type theory, we can formulate as dependencies, higher dependencies. A final comment. Small types form a two-fam category. There are specific arrows from two type families, the elements of this type. And one can show that every topos is a two-fam category in a natural way. And one can have two-fam categories, two-fam sigma categories, two dep-categories, and so on. And all these are satisfied by the extensions that we can show, can give in the example of topos. To conclude, I think that this specific, simple notion of dependent arrow looks like the way we define home sets. It generalizes these home arrows in case the family arrows are constant, and has all the basic characteristics that I find in the generalization of functions to arrows. Dependent arrows preserve many properties, important properties of dependent functions. They forget some of them, but they give us the opportunity to see new dualities, new constructions that the prototype cannot offer. And these constructions can be repeated. Thank you very much.